Well, good evening. The Thanksgiving weekend here in the US is almost upon us. So I wanted to get one last video in before that. I'm going to spend the next few days doing some work on my IoT devices and porting some code across from Arduino to the Windows 10 IoT core. So I thought, well, I'll just do a last little video on my 651B test oscillator. Now this is a fantastic piece of kit. It's very old school. I did a video on going into the whole item earlier on, and with the rearrangement of the lab and stuff like that, I don't think I'm going to keep it. I think I'm actually going to sell the unit. And what I wanted to do was to bring it up, make sure that it passes the manufacturer's specifications. So, to do that, I'm going to take it through the test. Now, I don't have some of the gear that they ask you to use, but I'm going to take it through the test and we'll see how it goes in terms of the performance test. So the first one up is the dial accuracy check, and this is the check to see how accurate the numbers here are on this dial versus the actual frequency that's coming out. Now this is my 53131A. This counter actually has the high stability time base option in it, and I've readjusted that to my GPS-DO. So it was very, very accurate in terms of being bang on a 10 meg source. So this information that you're seeing here on this display should be pretty damn good. So the first thing that I'm going to go do is set up to read this. So we want to get a frequency range of 10. So let's go in and set that as 10. We want the frequency dial to 1. So let's go in there and use this little vernier dial. This is a classic arrangement they have on a bunch of HP gear of this era. This is actually not a geared vernier in the sense that there's actually, sometimes what you get is a little vernier that drives a set of gears that drives against the main shaft. This is actually just simply a friction vernier that works on the edge of the dial. Anyway, let's dial that in there. That looks pretty close to 1. Now output attenuator, 3 volts, yep. And I'm going to adjust the amplitude for 3 volts. So now that we've done that, we set the counter to read the period. So let's go period 1 and run that. In the test setup, if you look at the test setup diagram, you'll see that you have the oscillator running through a 50 ohm feed through into the electronic counter. That's because the counter wasn't a 50 ohm device, whereas on here I actually have the ability to set a 50 ohm termination. And I have that set up, so if we go look at the period, it says make sure that the period should indicate 100 milliseconds plus or minus 3 milliseconds. So if we look, we've got it set up as seconds, so there is 100 bang on for 1, so we know that our dial frequency is pretty good there. I go over here and I take it to 10, and let's just zoom that in, and then I should be 10 megahertz plus or minus 300k, so I should be anywhere from 9.7 to 10.3. And I'm inside that. So for the 10's dial accuracy is actually pretty good. So let me take this back down to like 10 hertz and take it back down to 1. And now I'm just going to go and zoom in on, let me see if you see this. If you notice this, you'll see that what I've got here is a little bit of wiggle on the meter. Now, I don't know if that is actually on the signal or on the amplitude of the signal or on the interference with the meter. Now, the reason I say that is if we come up here and you look, you'll see that our signal is bang on and it's not moving at all. You know, if I touch the, if I touch this, oh, actually the reason it's not moving is that it's actually not reading it at all. Hang on, let's bring that in. I think scroll that in, and you'll see the gate value will flash. And so basically, you can see that I'm pretty much not getting, I'm getting 10 and then into the millihertz of movement there. So it's not in a zero crossing, it's going to come, if anywhere, it's going to come in the amplitude. Now, this is set at 3 volts, so we read this bottom item here, and so each one of those little meter things is about a tenth of a volt RMS. So what I'm seeing is probably somewhere, in the 10 to 20 millivolts of a signal bouncing up and down. So let's see if we can catch that in the actual AC signal. And so what we're seeing here is for this, with the extra cables and stuff in, we're seeing a lot of it wobbling around, but if you look, that's 3.01, and then it's in the single digit millivolt range. So looking at this, that's not in the single digit millivolt range, because I should be seeing 1,000th of the distance between there, and I think that's quite a bit more. So I think what we're reading from this is that there is some amplitude variation on this, but for this type of device, it actually isn't that bad. They spec output flatness in terms of tens of millivolts on this unit, so it is roughly acting flat in this particular case. So I think what we're reading in here, and I'm not a huge expert in these units, so I don't know, but I think what we're reading in here is some interference that is coming from the oscillator into the meter circuit. Alright, so the next check now is the output voltage check. So I leave everything connected up this way, and I set the frequency to be 1 kilohertz, the frequency dial to be 10. So let's go in and get 10 there, yep. And then the output attenuator to be 3. So let me just go get the, bam, yep, so we're on 3 there. And now I turn the amplitude controls fully counterclockwise. And what it says is that the output, the RMS output, should be 0.3 volts or less. And yep, we're actually 0.3 millivolts, so we're well down. We're supposed to be below 20 dB down. And now let's turn them all the way up. And it says I should be 3.16 volts or greater, and you'll see I'm in fact 3.39 volts, so we're good there. So now what I need to do is do the same thing, only with a 600 ohm load. So I happen to have a specific HP 600 ohm through terminator here. So let's take this guy off. Let's put this here, and then let's change this over to 600 ohms. Now, back in this era, they had a bunch of, they had a lot of equipment that would come out in both 50 and 600 ohm capabilities. And 50 was used for one type of stuff such as RF communications and so on. And I think 600 was used a lot in the audio industry or the telecommunications industry. I need to go have a little look at that. Well, that was interesting. I thought that the 600 ohm thing came from the audio and telecommunications industry, and in fact it does. And apparently, from a quick read of Wikipedia, the 600 ohm comes from not from any particular aspect about the cable or so on, but actually how they were connected into the exchange. If you remember back in the, well, you may remember back in the days of decadic dialing and having a mechanical exchange, there are phenomenal pieces of engineering. If you ever have the chance to go in and sit in one and listen to it operate, I don't think they run any anymore, but they were just classic noise producing things. Well, fundamentally that telecommunications relay connected via two coils, and those two coils were about 300 ohms each, and so that coil impedance gave the 600 ohm nominal impedance that the telecommunications industry needed. And if you match the output impedance with the load impedance, you're going to be able to put the biggest, longest cable on there that you can do. So that was sort of why the 600 ohms. Interesting aside there. Anyway, let's come back to the 600 ohm item there. We've done this, so now let's set this guy for 3 volts. So we'll go a bit past, and then I can fine tune down. And yep, I'm getting 3 volts. And so now, we'll take it all the way up, and I should be greater than 3.16, and I am. And then I should take this all the way down, and I should be less than 0.3, which I am. So the output voltage checks out. Now, technically, how this is supposed to actually work is, if you have a look here at the diagram, you can see that you have the test oscillator goes through a thermal converter, and then you create your own power supply, and you null it out using a DC voltmeter, a 419A. These thermal converters basically take the AC signal and they convert it into an RMS voltage, and they do that across a very wide range of signals. Now, I don't actually have, this calls for a 3 volt input one. I don't have one of those, but what I do have is this guy here. So let's see if we can zoom in and you can see the front of this guy here. Let me hold that a little bit closer. We'll just zoom out a bit, and you should be able to see that this is a 1 volt thermal converter. And so what I can do is I can put in an AC signal, and I can get out 7 millivolt output. So what I'm going to do is I'm going to take, let me zoom back out again, to check the flatness here. What I'm going to do is take the output of the unit, drop it into this item to the thermal converter, and then I'm just going to connect in my Keithley again. So we'll just put minus to minus, and then plus to plus, and there you can see that I have about so if I move this, say 0.8 volts, what I'm getting from here is 4.3. Now that isn't actually particularly interesting, per se. I'm not sure how linear these thermal converters are. I don't know what they do. But what we want to do, and this is what's going on here, is basically we're going to set a voltage here, and then we're going to create a reference voltage up here to get this to become 0. Now you can do that with modern multimeters by utilizing the relative function. So what I want to do is set for 1K. I'm going to go in and set this for 10 kilo ohms, 10 kilocycles, or kilohertz as the case may be. I'm kilocycles because I'm in it in that era. Now that I've got that set, I want to set for 1 volt, and what we're going to go do is we're going to go over here and we're going to select 1 volt and just put it bang on 1 volt. And you can see that what I should be getting, if I was getting A full 1 volt here is 7 millivolts. I'm getting 0.66, close enough for the purposes of what we're doing here, because that looks pretty much bang on. Now, rather than using a null meter, what I can do is I can actually just hit rel. And so now what we're going to go do is, as we change our frequency around, we're actually going to be measuring it relative to what we had set originally. And so what I should be trying to do is basically set a frequency and then set this and make sure that I'm back on the 1.0 item here. So rather than go through all that with you, I'm going to go do the first one and we'll watch that on video. Then I'll go do them all by myself, and we'll see. I'll let you know if they all pass. So the first one is going to be set for 10 Hertz. So now what I want to go do is I want to go and select 10 Hertz. Yeah, and then I'm going to adjust the amplitude control again so that I basically get my null. So let's go and see if I can drag that down a little bit. And that's pretty damn close. And that looks like it's on 1 volt there. Let's take a zoom in, and you can see the result when it zooms in. Let's see if we go macro and get it to actually zoom. It's very close to sort of thinking about it, but let's zoom back out again and put something in there. And the parallax error, let's get right down in front, and that, so you can sort of see that it looks pretty much bang on the 1 volt there. Okay, I have 2 more tests to do, and so this one is going to be the distortion level. And so what I'm going to go do here is I'm going to set, I can push these guys back a bit because in fact I don't need these guys anymore. What I'm going to do for the distortion test is set 1K to 1 here, and then 3 volts. So let's do 3 volts. Yep. And now I would plug this into a HP 331A distortion analyzer. I actually had one of those, and I did a video on it. And they work along the theory of basically looking at the entire spectrum. They were really regarded by HP. In fact, the one I had a little panel on it as being the first ever spectrum analyzer they did. And basically they look at all the signal sources and all the different frequencies, and then you put a notch filter in over the fundamental frequency that you are actually trying to measure. And that will then tell you what that gets away that fundamental frequency, and then what you're left with is basically all of the additional spurious signals that then effectively can add up to distortion. So I had one of those, but I sold that. What I have instead is an 8903B, and an 8903B is a proper audio analyzer, and so it actually has a bunch of different functions. But what it can do is it can actually come in and look at the signal and do all that work for us. So let's go take a look at that. And the beer for this evening is the Red Hook IPA Longhammer. It's a awesome IPA. It's not as hoppy as the standard ESB or the other beers. So give it a try. Alright, let's set up for looking at the other device. Okay, and here we are. What you can see here is the 8903A audio analyzer. It's telling me what frequency it's reading in, and it's also telling me what the AC level is for that. And so what I know from here is it's a 3 volt signal, and that's actually what I spec there. And it should be 1 kilohertz, which is what I've been asked to use. And so now, if I go in and hit distortion, it should actually go and calculate the distortion value for the signal at that frequency. And here you can see that the percentage distortion is 0.24%. And so according to the system, as long as I'm less than 1%, the system is great. Okay, so the last test that needs to be done is taking a signal from the 651B, running it through my instrumentation amplifier here, which we've looked at before, into a 355D attenuator, and then over here, Red Hook IPA, drink of choice, into my 34588, and basically what we're going to go do is just test whether or not the attenuator is working. So what we want to see is basically that number stays somewhere between 8.90 and 9.09 is pretty much where we want to see it go. So I'm going to zoom in on that, and basically what I'm going to go do is I'm going to turn the attenuator down and then take some attenuation off. And it's basically, the attenuator here is in 10 dB steps, and this is a 10 dB attenuator, so you can match them together. Okay, that's good. Let's go down again. But it looks like right at the bottom level we're a little out, and we may need to play around a little bit, or somebody may need to play around a little bit just on that attenuator flatness. But otherwise, it's pretty damn close across that entire range. So there you go. What we've done here is just go through the entire performance testing for a 651B. Hopefully you found that interesting, and you'll check out some of the videos on the channel. Anyway, catch you later. Happy Thanksgiving.